All right, so I'm continuing where I left off in the last video, and we're doing problem 9, the rest of the exercises. And so again, this is baby real analysis problems, and problem 9 took about 3 exercises that were taken from Bartle's Intro to Real Analysis 4th edition textbook, and they come from chapter 3, section 1. So I'm going to be doing the remaining 2 exercises that were from part 1. So this is exercise 7, and it says let xn, or the nth term of some sequence, be defined to be 1 over the natural log of n plus 1, where n is a natural number. Use the definition of the limit of a sequence or convergence of a sequence to show that the limit is going to be 0. And then part B is find specific values for capital N that guarantee the convergence when epsilon is 1/2 and epsilon is 1 over 10. Okay, so that's the problem. So xn, I'm just going to go ahead and write it. It's 1 over the natural log of n plus 1. We're going to show that this equals 0. So as n goes to infinity. So again, the definition of convergence. So some sequence an converges to some value a if and only if for all epsilon bigger than 0, there exists some capital N in the natural numbers such that for all little n bigger than capital N, we are within an epsilon distance of the limit. So the absolute value of an minus a is less than epsilon. So like the previous video and one before that, I'm going to first find the necessary index capital N. So strategy for finding capital N. So our sequence is 1 over the natural log of n plus 1. So we need the absolute value of 1 over ln n plus 1. And our limit's going to be 0 in this case. So minus 0 to be less than epsilon. All right, so that's going to be just 1 over, absolute value of 1 over the natural log of n plus 1. And again, n is a natural number, so this is going to be less than or equal to just 1 over natural log of n plus 1. Now recall that for the logarithm graph, it does like this, and it crosses the y-axis, or sorry, x-axis, and that's at the point 1 comma 0. And so when n is 1, the natural log of 1 is 0. So anything, our indices though, so we're dealing with the natural log of natural numbers. So we're really dealing with this portion of the graph. So it's going to be positive. Okay, so that's just keeping in mind sort of what, I guess, a sketch of what we're calling what the natural log graph looks like. Okay, so that's less than or equal to 1 over the natural log of n plus 1, and I need this to be less than epsilon. So if n is bigger than capital N, then the natural log of n plus 1, which is going to be greater than the natural log of n, since you're taking a bigger number of the natural log of, and the natural log of n is going to be greater than the natural log of capital N, since little n is bigger than capital N. So that's if and only if we can take the reciprocal of these, and it reverses the inequalities. Now keep in mind this is if capital N is bigger than 1, because we can't divide by 0. Okay, so that's needed because, again, we can't divide by 0. So then we have this is less than 1 over the natural log of lowercase n, little n, and that's less than 1 over the natural log of capital N. And we need this to be less than epsilon, and capital N is specifically going to be greater than 1. So we need 1 over the natural log of capital N to be less than epsilon. So we can take the reciprocal of both sides. So this is if and only if the natural log of capital N is greater than 1 over epsilon. So just taking the reciprocal of both sides, that's going to be natural log of capital N, and then the reciprocal of epsilon, 1 over epsilon, and flips the inequality. Now we want to get rid of the natural log so that we have it just in terms of n. So I could do e raised to both sides, since the exponential e and ln are inverses. So then that way the natural log goes away, and so we just have capital N needs to be greater than epsilon e raised to the 1 over epsilon. All right, so this is the n that we want. Okay, so now let's go ahead and do the proof. So again, this is just the first part of the problem. So proof, given epsilon bigger than 0, by Archimedean principle, we can find a capital N in the natural numbers. Such that capital N is bigger than e raised to the 1 over epsilon. So for all little n bigger than capital N, right, which is bigger than e raised to the 1 over epsilon, we have the absolute value of 1 over the natural log of n plus 1 minus 0, because that's what we're saying it converges to, and that's just equal to the absolute value of 1 over the natural log of n plus 1. And that's less than or equal to 1 over the natural log of n plus 1. And we said this is going to be less than 1 over the natural log of little n. And this is going to be less than 1 over the natural log of capital N. And again, capital N is bigger than 1. You don't necessarily need to state that because e raised to 1 over epsilon. So we need capital N, the index, to be greater than 1 so that we're not dividing by 0. So 1 over the ln of capital, 1 over the natural log of capital N, that's going to be less than, let's see, so to be kind of off to the side. So since n is greater than e raised to the 1 over epsilon, then the natural log of n, capital N, is greater than the natural log of e raised to the 1 over epsilon. And that implies 1 over the natural log of capital N is less than 1 over the natural log of e raised to the 1 over epsilon. And so we have 1 over the natural log capital N to be less than 1 over the natural log of e raised to the 1 over epsilon. Well, by logarithm rules, right, that's going to be equivalent to 1 over epsilon. And they're taking the reciprocal of 1 over epsilon that gives you epsilon. Okay, so that is the proof of convergence for part A, showing that our limit is 0. Now part B wants specific values for n. And part 1 of part B, so that's going to be using epsilon being 1/2. And then part 2 is using epsilon being 1/10. Well, we know capital N is going to be bigger than e raised to the 1 over epsilon. So for part 1, you're going to need n to be greater than e raised to the 1 over 1/2, which is just e squared. Okay, then I'll just use the calculator. All right, so what is e squared? So let me clear that. E squared, so second, and then that's 7.38. So any capital N that's beyond this number, so we could use capital N to be 8. Okay, so that's our answer for part 1. Now part 2, we need capital N to be greater than e raised to the 1 over 1/10. Well, that's basically n greater than e raised to the 10th. So let me clear this. Okay, so e raised to the 10th. So that's this number, 22,026.46579. So a natural number bigger than that, 22,027. All right, so that's the index we need. So that for all the indices beyond this, we're going to have the convergence when epsilon is 1 over 10. All right, so that is that example. I have one more example or exercise for problem 9. All right, so this is exercise 8. This was the last exercise for problem 9. And we're proving that the limit of some sequence xn equals 0 if and only if the limit of the sequence of the absolute value of xn also equals 0. And then give an example example in which the convergence of the sequence of the absolute value of xn does not imply necessarily the convergence of the sequence xn. So this is an if and only if proof. So I'll do this direction first. So I'll assume the limit of just the sequence xn equals 0 and show that that is going to imply that the limit of the absolute value of xn is also 0. So let's, again, I got to have some epsilon that's given. So given epsilon. So since our sequence xn converges, so since xn converges to 0, there's some capital N such that for any little n bigger than capital N, we have the absolute value of xn minus 0 less than epsilon. All right, that's what we know, since we have this for our sequence xn converging to 0. So this part doesn't, I'm going to use the corollary, and I'll write the corollary to the triangle inequality. Not sure if that's how you spell it. So corollary to the triangle inequality is that if you have the absolute value in which you have the absolute value of A minus absolute value of B inside of that absolute value, that's less than or equal to the absolute value of A minus B. All right, so based on this corollary, and that's just, I just wanted to state it first. So based on the corollary to the triangle inequality, we have the absolute value and the absolute value of xn minus the absolute value of 0 is less than or equal to the absolute value of xn minus 0. And we already know xn minus 0, that absolute value is less than epsilon. And so we've basically shown that the absolute value of the sequence xn converges to 0 also. So using this same end that guaranteed the convergence, we have the absolute value of xn minus 0, since that's the absolute value of 0, 0, is less than epsilon. So that tells us the sequence of the absolute value of xn converges to 0. All right, so that was using this n that we know capital N from based off of the sequence xn converges to 0. We already know that the absolute value, the difference of xn minus 0 is less than epsilon. So then the corollary to the triangle inequality, we have the absolute value of xn minus absolute value of 0, which is the same thing as the absolute value of xn minus 0, less than or equal to our absolute value of xn minus 0 that we already know, that is less than epsilon for that capital N. So we just use the same thing and apply the corollary. All right, so that is the proof in that, for that part. Now we're going to do the proof in the other direction. So now we're going to assume that the limit of the absolute value of xn is 0. And we need to show that the limit of just the sequence xn is 0. All right, so before I do the proof, there is some theorem I'm going to use. And I've used this in the lecture series videos, and I called it like some useful theorem. So this was used in, if you've watched the playlist. I didn't state where the theorem came from, but this is specifically theorem 1.29 from Bartle's textbook. If you do have it. But I just said in the video, it's just some useful theorem I applied in a proof. I believe in proving that the infimum of 1 over n is 0. I think that was the video in which I applied this theorem. So the theorem basically says if you have a real number a, so if a is some real number such that 0 is less than or equal to a, which is less than epsilon for any epsilon bigger than 0, then that means a is also 0. So then a itself is 0. And you'll see once I work out the proof how I'll be applying this theorem. All right, so resuming to the proof. So since, let's see, so first let me address that we're given some epsilon. So given epsilon, all right, since the sequence of the absolute value of xn converges to 0, we know there's some n, some capital N, such that for all little n, bigger than capital N, we have that the absolute value of xn minus 0 is less than epsilon. So that's what we know. We're going to eventually show that the sequence xn is also going to have 0 as its limit. All right, so the absolute value of xn minus 0. So this is if and only if the absolute value of xn is less than epsilon. By our definition of absolute value with inequality, this is if and only if we have negative epsilon less than the absolute value of xn, which is less than epsilon. But then absolute value of xn is, it's positive. It could be positive or 0. So really, we have 0 is less than or equal to the absolute value of xn less than epsilon because of the absolute value of xn. All right, so what does this mean? So at some point, so at some n, the terms in which the indices are bigger, little n are bigger than capital N. So it's at some n, we have that based on this theorem 1.29. So for if a is a real number where a is less than, or 0 is less than or equal to a, less than epsilon for any epsilon, then we can use this. It's just now instead of a, I'm using the absolute value of xn. So based on theorem 1.29, we have that the absolute value of xn is 0. All right, so again, still using this capital N. So that equals 0. And then if and only if xn is 0, right? So the absolute value of something being equal to 0 has to be that that something in which you're taking the absolute value of is itself equal to 0. So that's if and only if xn equals to 0. So again, using this same capital N, we have for all little n bigger than capital N, the absolute value of just xn minus 0 is going to be pretty much just equal to the absolute value of 0, because xn is 0 for this particular cutoff point. So then that's going to equal the absolute value of 0, which is less than epsilon. So that completes the proof. All right, so again, this direction, I assumed that the limit of the absolute value of the terms of xn is 0. So given epsilon, there's some capital N, some index capital N, where for all the indices beyond that, we have the absolute value of xn minus 0 to be less than epsilon. Well, that's if and only if the absolute value of xn less than epsilon. And that's if and only if, just based on definition of absolute value with inequality, that we have negative epsilon less than the absolute value of xn less than epsilon. But since xn, we're having an absolute value of that, that's greater than or equal to 0. So really we have 0 less than or equal to the absolute value of xn less than epsilon. All right, so, and again, I'm emphasizing that it's at some point capital N. So as long as you reach that point, that's what happens. So that's going to be the absolute value of xn equals 0 because of the theorem 1.29. All right, so then if the absolute value of xn is 0, then xn itself is 0. So using that particular capital N, we have for all little n bigger than capital N, the absolute value of xn minus 0, which is going to be equal to the absolute value of 0, which is less than epsilon. All right, so that completes the proof. Now the last bit of the problem is to give an example where the convergence of the absolute value of sequence xn, so where this converges but does not mean the sequence of xn converges. And a simple example, I think, is just to have the sequence xn where it's equals either -1 or 0, or let's see, I'll define it, sorry. So xn equals -1 to the n power. And again, n is some natural number. So xn is going to be, so you have a sequence where it's alternating with -1 and +1, right? So -1 to the first power is -1, -1 squared is +1, and then it just keeps alternating. So the sequence does not converge to a particular limit. So xn does not converge. Since depending on what n you're at, xn either goes to 1 if the n you're at is even, or the sequence is -1 if you have an odd value for n. So there's no particular value for which the sequence converges to since it has that alternation. All right, so the sequence xn converges, but the absolute value of xn, so you're taking the sequence of the absolute value of -1 to the n, well then that's always going to be +1. All right, so you're taking the absolute value of -1 raised to any exponent that's a natural number. It's going to always give you 1. So this is really the sequence of 1s. And so the sequence of 1s, well, it's all once a constant sequence, so it converges to 1. So we have that the convergence of xn, so that converges, but the regular sequence xn does not converge. All right, so hopefully that example, I think the example makes sense. I'm hoping the proof for this problem or this exercise made sense.